The best practice recommendation for grounding and surge protection of telephone entry systems at remote gates is to install a ground rod next to the entry panel and bond it to the local electrical service ground. This approach provides multiple grounding paths for electrical faults and lightning surges. Bonding the ground rod to the electrical service ground creates these multiple pathways, reducing the risk of damage to the entry system and associated equipment. Additionally, bonding the ground rod to the electrical service ground helps mitigate ground loop noise, which can interfere with telephone and data signals. A dedicated ground rod provides a low resistance path for lightning current to dissipate into the earth, protecting the entry system from lightning strikes. By bonding the ground rod to the electrical service ground, this protection is extended to other connected equipment. When installing a ground rod, the ground rod should be a copper-clad steel rod 8 feet long and driven at least 6 feet into the ground. Use a heavy-gauge copper wire, for example number 6 American wire gauge, to bond the ground rod to the electrical service ground. If the electrical service grounding system is at the main service entrance, which is significantly distant from the entry system, a grounding electrode system inspection should be performed to ensure the system's integrity and meet code requirements. An alternative option of installing a ground rod only provides a limited grounding path and may not be sufficient for lightning protection. Grounding the entry panel to the local electrical service ground without a dedicated ground rod may not provide adequate lightning protection, especially in areas with high lightning activity and high ground resistance. Considering the environment and the equipment requiring protection, a combined approach is the best option. This involves installing a dedicated ground rod near the entry panel and then properly bonding it to the electrical service ground. This method offers a multifaceted approach to grounding and surge protection. Firstly, it provides multiple grounding paths, which is crucial for both electrical faults and lightning surges. These redundant paths ensure that if one path is compromised, others are available, minimizing the risk of damage to the entry system and its connected equipment. Secondly, it mitigates ground loop noise. Ground loops can introduce unwanted noise into telephone and data signals, disrupting communication. Bonding the ground rod to the electrical service ground helps to equalize the ground potential, thereby reducing the likelihood of ground loop formation and the associated noise. Thirdly, it enhances lightning protection. A dedicated ground rod offers a low resistance path for lightning current to dissipate into the earth. This direct path minimizes the voltage buildup within the system, protecting sensitive electronic components from damage due to lightning strikes. Further extending this protection is the bonding of the ground rod to the electrical service ground, which creates a unified grounding system that protects not only the entry system but also other interconnected equipment. When installing the ground rod, it should be a copper-clad steel rod that is 8 feet in length. The rod must be driven at least 6 feet into the ground to ensure good contact with the earth. To bond the ground rod to the electrical service ground, use a heavy-gauge copper wire. A number 6 American wire gauge wire is commonly recommended. The connection should be made using appropriate grounding connectors that are listed for direct burial. If the electrical service grounding system is located at the main service entrance, which is a considerable distance from the entry system, then a grounding electrode system inspection should be conducted. This inspection verifies the integrity of the existing grounding system and ensures that it meets all applicable code requirements. The inspection should include checking the resistance of the grounding electrode system to ensure it is within acceptable limits. Also consider surge protection devices. In addition to proper grounding, surge protection devices, or SPDs, should be installed at the entry panel. These devices help to divert transient voltage surges away from sensitive electronic equipment, providing an additional layer of protection against lightning strikes and other electrical disturbances. These SPDs should be properly rated for the voltage and current levels of the system they are protecting. There are alternative approaches, however, they are not as effective as the combination of a ground rod and bonding to the electrical service ground. Installing a ground rod alone offers a limited grounding path and may not be sufficient to provide adequate lightning protection. Grounding the entry panel directly to the local electrical service ground without a dedicated ground rod might not provide sufficient lightning protection, especially in areas prone to frequent lightning activity or characterized by high ground resistance. The combination of a dedicated ground rod and bonding to the electrical service ground is the preferred method. The grounding electrode system, often referred to as GES, comprises all interconnected grounding electrodes at a facility. These electrodes can include ground rods, ground plates, metal underground water pipes, and the building's metal frame, if it is effectively grounded. The purpose of the grounding electrode system is to provide a low impedance path to earth for fault currents and lightning surges, thereby protecting equipment and personnel. Ground rods are typically copper or copper-clad steel rods that are driven into the ground to establish a direct connection to earth. The length and diameter of the ground rod, as well as the depth to which it is driven, are determined by local electrical codes and site-specific conditions. The minimum length of a ground rod is typically 8 feet, and it should be driven vertically into the ground so that at least 8 feet of the rod is in contact with the soil. Ground plates are another type of grounding electrode that consists of a metal plate buried in the ground. These plates are typically made of copper or galvanized steel and are available in various sizes. Ground plates are often used in situations where it is difficult to drive a ground rod, such as in rocky or paved areas. Metal underground water pipes can also serve as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. However, the use of metal underground water pipes as grounding electrodes is subject to certain restrictions and requirements, as specified in the National Electrical Code, or NEC. The building's metal frame can be used as a grounding electrode if it is effectively grounded and meets certain requirements. The metal frame must be connected to the grounding electrode system with a low impedance conductor. The grounding electrode conductor, often referred to as GEC, is the conductor used to connect the grounding electrode to the equipment grounding system or to the grounded conductor at the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code. The grounding electrode conductor should be copper or aluminum and must be installed in a manner that protects it from physical damage. The equipment grounding system is a network of interconnected conductive pathways that provide a low impedance path for fault currents to return to the source. The equipment grounding system includes equipment grounding conductors, metal enclosures, and other conductive parts of electrical equipment. The purpose of the equipment grounding system is to provide a safe path for fault currents, thereby minimizing the risk of electric shock and equipment damage. Equipment grounding conductors, often referred to as EGC, are the conductors used to connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. The size of the equipment grounding conductor is determined by the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor should be copper or aluminum and must be installed in a manner that protects it from physical damage. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to the connection of electrical equipment to the earth, while bonding refers to the connection of non-current carrying metal parts of electrical equipment to create a low impedance path for fault currents. Grounding is intended to provide a path for fault currents to return to the source, while bonding is intended to minimize voltage differences between metal parts of electrical equipment. Surge protection devices, often referred to as SPD, are devices designed to protect electrical equipment from voltage surges or transient overvoltages. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. Surge protection devices work by diverting the excess voltage away from sensitive electrical equipment, thereby preventing damage. Surge protection devices are typically installed at the service entrance, at branch panels, and at individual equipment locations. There are three main types of surge protection devices: Type 1, Type 2, and Type 3. Type 1 surge protection devices are installed at the service entrance and are designed to protect the entire facility from voltage surges. Type 2 surge protection devices are installed at branch panels and are designed to protect specific circuits or equipment. Type 3 surge protection devices are installed at individual equipment locations and are designed to protect sensitive electronic equipment from voltage surges. The National Electrical Code, often referred to as NEC, provides comprehensive requirements for grounding and bonding of electrical systems. The NEC specifies the types of grounding electrodes that are permitted, the size of the grounding electrode conductor, the requirements for the equipment grounding system, and the requirements for surge protection devices. Compliance with the NEC is essential to ensure the safety of electrical systems and to minimize the risk of electric shock and equipment damage. NEC Section 250.4 addresses general requirements for grounding and bonding, emphasizing the creation of a low impedance path for fault current to facilitate the operation of overcurrent devices. NEC Section 250.24 covers grounding of service-supplied alternating current systems, outlining requirements for grounding the neutral conductor and connecting it to a grounding electrode system. NEC Section 250.50 details the grounding electrode system, specifying acceptable grounding electrodes such as ground rods, metal water pipes, and building steel, and how they should be interconnected. NEC Section 250.66 specifies the size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Section 250.104 addresses bonding of metal water piping, metal gas piping, and other metal parts that may become energized, ensuring a low impedance path for fault current. NEC Section 250.122 specifies the size of equipment grounding conductors based on the rating of the overcurrent protective device. NEC Section 285 covers surge protective devices, outlining requirements for their installation and performance. The grounding electrode system should have a resistance to earth of 25 ohms or less, as measured using a ground resistance tester. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. Grounding conductors should be protected from physical damage by installing them in conduit or by using other protective measures. Grounding connections should be made using approved connectors and fittings that are listed for grounding purposes. All electrical equipment should be properly labeled to indicate that it is grounded. Regular inspections and testing of the grounding system should be conducted to ensure that it is functioning properly. Any deficiencies in the grounding system should be corrected promptly. Proper grounding and bonding are essential for electrical safety. By following the requirements of the National Electrical Code and by implementing best practices for grounding and bonding, you can minimize the risk of electric shock and equipment damage. It is important to consult with a qualified electrical contractor or engineer to ensure that your electrical system is properly grounded and bonded. Ground resistance testing is a crucial part of maintaining a safe and effective grounding system. It involves measuring the resistance between the grounding electrode system and the surrounding earth. A low resistance indicates a good connection to earth, which is essential for dissipating fault currents and protecting against electrical shock. The fall of potential method is a common technique used for measuring ground resistance. It involves driving two auxiliary electrodes into the ground and a line away from the grounding electrode under test. A ground resistance tester is then used to inject a test current between the grounding electrode and one of the auxiliary electrodes, while measuring the voltage drop between the grounding electrode and the other auxiliary electrode. The measured voltage and current are then used to calculate the ground resistance. The three-point test method is another technique used for measuring ground resistance. It involves driving two auxiliary electrodes into the ground at right angles to each other, with the grounding electrode under test at the corner of the angle. A ground resistance tester is then used to measure the resistance between the grounding electrode and each of the auxiliary electrodes. The measured resistances are then used to calculate the ground resistance. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. It is an important factor to consider when designing a grounding system, as it affects the effectiveness of the grounding electrodes. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. Sandy soils typically have higher resistivity than clay soils. Wet soils have lower resistivity than dry soils. Warm soils have lower resistivity than cold soils. Soil resistivity can be measured using a soil resistivity meter. The 4-point Wenner method is a common technique used for measuring soil resistivity. It involves driving 4 electrodes into the ground in a straight line at equal intervals. A soil resistivity meter is then used to inject a test current between the 2 outer electrodes, while measuring the voltage drop between the 2 inner electrodes. The measured voltage and current are then used to calculate the soil resistivity. Electrolytic grounding is a technique used to improve the effectiveness of grounding electrodes in areas with high soil resistivity. It involves surrounding the grounding electrode with an electrolytic solution, which helps to reduce the resistance between the electrode and the soil. Electrolytic grounding can be particularly useful in rocky or sandy soils where it is difficult to achieve a low ground resistance. Chemical ground rods are a type of grounding electrode that contains a chemical compound designed to improve the conductivity of the surrounding soil. These ground rods are typically used in areas with high soil resistivity or where it is difficult to drive a conventional ground rod. The chemical compound slowly leaches into the soil, creating a conductive path between the ground rod and the earth. Grounding system design involves selecting the appropriate type and size of grounding electrodes, determining the optimal location for the electrodes, and calculating the required size of the grounding conductors. The design process should take into account the soil resistivity, the size and type of electrical equipment being grounded, and the applicable electrical codes and standards. A qualified electrical engineer or contractor should be consulted to ensure that the grounding system is properly designed and installed.